Hello and welcome to Insight Ophthalmology. I am Dr. Amrit welcoming you to another live stream. Today we are talking about numerical MCQ based problems on the Snellen's chart. So in this video we shall be discussing 6 high yield problem based MCQs on Snellen's visual acuity, and each problem will have 4 multiple choices. The viewer is expected to give the correct answer within 10 seconds of each question. After that the correct answer will be revealed and the explanation will follow. Also, it's advised that you keep a pen and paper handy for calculations. Before we dive into some of these high yield Snellen chart problems, make sure that you hit that subscribe button if you haven't already. And by subscribing, you get access to our live chat wherein you can ask all your questions as we go along. And don't forget to share this session with your friends, colleagues, or anyone who you think would love to solve these problems together. And it's going to be a fun and interactive session, hopefully. Also, if you have any doubts or questions later on, you can feel free to drop them in the comment section. We'll be sure to get to them after the live session. Alright, so let's get started and let's tackle some of these Snellen chart challenges. The first problem is the Snellen chart is basically based on the eye's ability to resolve details. So what is the minimum resolvable angle for a person with 6 by 6 vision? Your options are 1 minute of arc, 2 minutes of arc, 5 minutes of arc, or is it 10 minutes of arc? The timer starts now.
I was lost until I found that I'm invincible. Nobody gonna bring me down.
Alright, so I hope you are ready with your answers, and the correct answer to this problem is 1 minute of arc. So really congratulations to all of those who got it right, and for those who couldn't get it right, don't worry, I'll try to explain it to you. Now basically the Snellen's visual chart usually can be denoted in 6 meters notation or 20 feet notation. Now each row, as you can see, is basically represented in the form of a fraction here. So you have a numerator and you have a denominator. The numerator here represents basically the distance at which the patient stands from the Snellen's chart. It could be 20 or it could be 6 meters. The y, that is the denominator, basically represents the distance at which a person with normal visual acuity should correctly identify the letters. So what I mean to say is, if 6 by 60 is written here, 6 means that the patient is standing at a distance of 6 meters from the chart, and 60 means that the 6 by 60 letter should be seen by a patient with normal visual acuity clearly from a distance of 60 meters. Alright, so that is one very important thing. Then each of these letters, if you see, they are made up of these bars, and these small bars will also subtend an angle of about 1 arc minute at the nodal point of the eye. And then we have the spaces, intervening spaces as well in between. Those spaces also subtend an angle of 1 arc minute at the nodal point of the eye. The Snellen's chart itself is based on the theory that the smallest object which can be resolved by the eye subtends an angle of about 1 arc minute at the nodal point of the eye, right? Now over here you can see this bar is 1 arc per minute. This space is again 1 arc per minute. This is again 1 arc, again 1 arc, and again 1 arc. So you have this 5 into 5 grid structure superimposed on every letter of the Snellen's chart, such that each stroke and each space subtend an angle of 1 minute of arc resolution per element, and in total it becomes 5 minutes of arc, right? So this 1 minute of arc resolution per element is the standard resolving power for a person with 6 by 6 vision, right? So this was a very simple problem on minimum angle of resolution. We will have one more problem on minimum angle of resolution later on at the end of the live session. All right, let's go ahead and talk about the second problem. Here, the question is, a person is standing at 6 meters distance from the Snellen's chart and is looking at a letter on the 6 by 36 line. The question is, what is the angle subtended by this letter on the 6 by 36 line at a distance of about 6 meters? And if the person moves to 3 meters now, what will be the new angle subtended? Alright, so take out your pen and paper and try solving it. Now let me put up the 10-second timer on. Alright, so are you ready with the answers? So let me tell you that don't get disheartened if you're not able to solve the problems within 10 seconds. It's just an arbitrary timer. You can pause the video and you can take your time, solve the question, because this is not really a test. This is something that we are practicing. We're trying to clarify our concept. So take your time, pause the video and then restart the video. Alright, so what is the correct answer here? The correct answer is A, that is 30 minutes of arc at 6 meters and 60 minutes of arc, that is 1 degree at 3 meters. So for those of you who got it right, congratulations, and those who didn't, let me try to explain it to you. So the key rule that you have to remember in order to solve such problems is that each letter on a Snellen's chart subtends 5 minutes of arc angle at its denominator distance. That is the second number in the fraction. For example, you can see over here there are different letters here. The first letter is the 6 by 60 letter, or 20 by 60, let's say. So this means that this letter is going to subtend the angle of 5 minutes per arc, or 5 arc minutes, at a distance of 60 feet. Similarly, a 20 by 40 Snellen's line letter indicates that this E, or this letter, will subtend 5 arc minute at what distance? At a distance of 40 feet. 20 by 20 Snellen lines means that at 20 feet, this letter E will subtend an angle of about 5 arcs minute. So that is very important. Whatever you have in the denominator, that is the distance where 5 arcs per minute would be subtended. Similarly, if you take the 6 meters notation as well, a 6 by 6 letter will subtend the same angle at 6 meters. 6 by 12 letter will subtend this 5 minute arc angle at 12 meters, and 6 by 36 letter will subtend this angle of 5 arc minute at 36 meters, right? Moreover, if the observer is closer to the Snellen's chart, what will happen? The visual angle will increase, and if the observer is farther from the Snellen's chart, the visual angle is going to basically decrease. Alright, so let's see how this problem can be solved. So over here, you can see that initially the patient is standing, or the person is standing at 6 meters from the Snellen's chart, and the letter that he's looking at is 6 by 36 line. So what did I tell you? 6 by 36 basically means that at 36 meters distance, the angle subtended by this letter would be how much? Would be 5 arcs per minute. Now the question says that what is the angle subtended by this letter at 6 meters? It's very simple. Now the person is moving closer. So the distance is decreasing, right? And by how much times are we decreasing the distance? We are decreasing it basically 6 times. How do you know that? You simply divide them, right? So 36 divided by 6 is 6 times. You are decreasing the distance 6 times. And as you decrease the distance, the angle is going to increase. And here the angle will increase by 6 times. So you multiply the angle by 6 and you get 5 6 is what? It is 30. So at 6 meters, you will get 30 arcs minute, right? So let's tackle the second part of the question. So if the person now moves to 3 meters, what will be the new angle? So at 6 meters, what angle did you get? You got it as 30 arcs per minute. Now let's say the person moves closer, that is 3 meters. That means the distance has been now what? It has been halved. So now the angle will become twice, and therefore it will become 60 arcs minute. Alright, and that's the reason why the correct answer was 30 minutes of arc and 1 degree, or 60 minutes of arc at 3 meters. Now you might ask, what is this 1 degree? So for that you need to know some important conversions. 1 degree is equal to 60 minutes of arc, and therefore as we got the answer as 60 minutes of arc, you can also write it as 1 degree. Similarly, at 6 meters you got 30 minutes of arc, so that is about 0.5 degrees. Alright, so I hope that is clear. Don't fret about it. Practice will make you perfect. So let me give you one more question to practice. This is the third problem. So a person is standing at 12 meters now from the Snellen's chart and he's looking at a letter on the 6 by 12 line. Now you need to tell me what is the angle subtended by this letter at 12 meters, and if the person moves to 4 meters, what will be the new angle subtended? So the timer starts now.
Until I found that I'm invincible. Nobody gonna bring me down.
Okay, so were you able to answer, give the correct answer? Let us see. So first let me try to solve this question for you. So here the person is standing at 12 meters from the Snellen's chart and looking at a distance of 6 by 12 line. The question is very simple. What is the angle subtended by this letter at 12 meters? Very simple. 6 by 12 means, what did I tell you? At 12 meters, the angle subtended by this letter would be how much? 5 arcs per minute. And this gives you the answer to your first part. So the first answer should be 5 arc minute. Now the question is, the patient has moved, or the person has moved to 4 meters. That means the distance has been decreased by how much times? 3 times, right? Distance has been decreased 3 times and therefore the angle will increase 3 times and therefore the angle will now become 15 arcs per minute. Okay, be very careful with your calculations. So if one thing is decreasing, the other thing has to increase, right? Okay, so the correct answer here is 5 minutes of arc and 15 minutes of arc. So congratulations to all of you who got it right. Well done. Problem number 4. Now you are looking at the topmost letter on the Snellen's chart. And what angle does this letter subtend at 6 meters? So that's the question. Is it 50 minutes of arc? Is it 60 minutes? Is it 30 minutes of arc? Or is it 10 minutes of arc? So the timer starts now. Come on. And the correct answer is 50 minutes of arc. So again, congratulations to all of you who got it right. And for others, let me explain it to you. It's very simple. I'm talking about the topmost letter. The topmost letter is 6 by 60 letter, right? Now, what do you know? At 60 meters, the angle subtended by this letter is usually 5 minutes of arc. And we are simply asking what is the angle subtended at 6 meters. So basically from 60 meters, you are coming down to 6 meters. That means the distance is being reduced by 1/10 and therefore the angle is going to be increased by 10 times. So initially if it was 5, it will become 50 now. And therefore the final answer is the 6 by 60 letter or the topmost letter subtend an angle of 50 minutes of arc at 6 meters. Alright, so practice makes you perfect, so don't worry about it. The next question is, a 6 by 12 letter on the Snellen's chart, what angle does it subtend at 6 meter? Your timer starts now. Alright, so what's the answer? I hope you're not just guessing here and you're actually solving. The correct answer is 10 minutes of arc. So very well done to all of you who got it right. So do I need to solve it again? So the question is 6 by 12 letter on the Snellen's. So here 6 by 12 means at 12 meters the angle will be how much? 5 arcs per minute. Now the question is for 6 meters. That means the distance is being halved and therefore the angle will be doubled. So the answer is 10 arcs per minute. Alright. Now the last question is, a person has a visual acuity of 6 by 24. Now what is their minimum angle of resolution? So here the options are 2, 4, 6 or 10. The timer starts now. Now this might look difficult, but it is really not. So the correct answer is 4 here. I hope all of you got it right. So how do we basically calculate the minimum angle of resolution? The minimum angle of resolution is nothing but it is the reciprocal of what? It is the reciprocal of visual acuity. The visual acuity has this numerator and denominator. So 1 divided by visual acuity will become your minimum angle of resolution. So here the denominator of the Snellen's fraction will come on top, and that you have to divide with the numerator. For example, here let us take 6 by 6. Here the numerator and the denominator are both same. So you divide the denominator by the numerator and you get 1. Similarly 6 by 12. So minimum angle of resolution will be denominator, that is 12, divided by numerator, that is 6. So that becomes 2. Okay, it's very simple. Similarly for 6 by 24 it will become 4. For 6 by 36 it becomes 6. For 6 by 60 it becomes 10, because 60 divided by 6, right? So the first question I told you, minimum angle of resolution is about 1. And since each element, since basically there is a 5:5 grid, so the total angle that is subtended at the nodal point by each letter would be about 5 arcs per minute, and the distance at which this 5 arcs per minute will be formed is represented by the denominator in the Snellen's visual fraction. So I hope that is clear. All right. So remember this 1, 5, and remember the importance of denominators, and you should also know how to calculate the minimum angle of resolution. So I hope that is correct. So practice will make you perfect. Again, if a person can resolve details at 6 meters that a normal person sees at 60 meters, what is their minimum angle of resolution? So a hint that I would like to give it to you over here is, first you try to calculate the visual acuity of the person, and then you calculate the minimum angle of resolution. The options are 6, 8, 10 or 12. The timer starts now. Alright. So what's the answer? The answer is 10. Okay, so congratulations to all of you who got it right. It was basically a very simple question. I told you that the person is able to, let me just put the answer question here. So I told you that this person can resolve the details at 6 meters what a normal person sees at 60 meters. That means his visual acuity is how much? It is 6 by 60. And what is the minimum angle of resolution? It is 1 divided by visual acuity, and therefore here it will be 60 by 6, that is 10. So hope you found this session useful and you feel now more confident in solving any Snellen's chart problems now. So I made this video because I was getting a lot of questions directly in the comment section. So for those who are still a bit unsure of it, don't worry, you can practice them again. If you simply enjoyed this session, you might also like to check out more in-depth content on the Snellen's chart right here on the channel. Make sure to check it out and let me know if you have any more questions. I'm always here to help you out. Now let's do one thing, that we'll start playing this video on decoding visual acuity testing now, and you can go ahead and watch this video, and if you have any doubts you can put it in the comment section or in the live section. I'm right here with you and I'll be answering your queries in the live chat. Thank you for staying connected. Thank you and have a nice day. So before you understand the concept of visual acuity properly, we should understand that what is meant by visual angle. The visual angle is the angle which is subtended by an object that we are looking at the nodal point of the eye by this object. So if this is the object present in the visual field, the physical dimensions of this object, in particularly the height of this object, and also depending upon the distance at which this object is located, this object will be subtending an angle or will be making an angle at the nodal point of the eye, and this angle is referred to as the visual angle. Now, you may ask now what is meant by the nodal point. The nodal point is roughly located between the anterior 2/3 and the posterior 1/3 of our crystalline lens. So if you understand what is meant by visual angle, now I will tell you what is meant by visual acuity. Now, in a very loose language, or to describe very simply, visual acuity is basically the measure of ability of the eye to distinguish between the various shapes and the details of the object which are given to it at a given distance. So in other words, it is the resolving power of the eye. The resolving power or the resolution means to be able to distinguish two objects as two separate objects in a space. So if we have object A and object B, two present in our visual field, we should be able to distinguish these two as two separate objects, and that is called resolution or the resolving power of the eye. To give a proper definition of the visual acuity is actually the reciprocal of the minimum resolvable angle measured in minutes of arc for a standard test pattern. So I told you what is meant by the visual angle. So for a very minimum amount of visual angle, we'll be able to resolve, and that is called a minimum resolvable angle. The reciprocal of that minimum resolvable angle and the units for that is minutes of arc will give you what is meant by visual acuity. So what are the components of visual acuity? Now there are a few terms that you should understand before you understand the depths of visual acuity. What is meant by minimally detectable? What is minimum separable, minimum cognizable, and minimum discriminable? The minimum detectable means that the ability to determine whether or not an object is present in the visual field. That means you are just detecting the presence of the object in the visual field. That means if this is the visual field, whether this white dot is present or not, whether this white line is present or not, and again this black dot and black line are present or not in the visual field. So that is called the minimum detectable acuity, right? So for this kind of acuity, the limit is 1 arc second. Okay, next. Now here is the other term which is called minimum separable. Minimum separable, as I told you, two objects which are separated in a spatial in a space, and you should be able to identify them as two separate objects, right? So there are two, like for example here we have two dots and they're separated by a distance. So this is called minimum separable, and this is also referred to as a resolution, right? So what is a threshold, or what is the minimum angle, visual angle that the object should subtend at our eyes so that the objects are at least minimally separable? The angle is 30 to 60 seconds of an arc, right? So this is the minimum angle of resolution, and the reciprocal of this angle only will give you the visual acuity, because visual acuity is the resolving power of the eye. So similarly, in the second picture, you can see there are 5 lines, and you're able to tell that there are 5 lines and they are separated. That means they are not overlapping. So what I mean by minimum angle of resolution is that if the angle, or if the visual angle subtended by two objects, okay, falls below this below this minimum angle of resolution, that is below 30 to 60 seconds of arc. That means if the angle subtended is about 20 or 10, then you'll not be able to resolve that object in the space. You'll have actually you will perceive it as overlapping or one single object instead of perceiving it as two different objects. Next is, once the brain is able to resolve a particular object, then it can also recognize it, right? So when we give the patient or give an examinee certain objects which are familiar to it, like letters E, A, B, like that, or some symbols like this, okay, then we are testing the recognizing ability of the patient. That is called minimum cognizable. So not just the detection and then resolution, but also the recognition ability of the patient is tested during the visual acuity. And then this is usually not done, and this is called the minimum discriminable. Minimum discriminable means that it is the ability to determine whether or not two parallel or straight lines are aligned in a frontal plane. So if you see, there is this one line and there is this two lines, and you can see there is a small offset between that. That means the two lines are not aligned in a straight line. So this, if you're able to detect this minor offset of the lines, then this is called hyper acuity or super acuity, right? So this is even more advanced acuity. Now, just for the completion's sake, a common question which is asked is, what are the components of measurement of vision? So the components of vision are the visual acuity, the visual fields, contrast sensitivity, color vision, and stereopsis, that is the binocular single vision. Now, let us talk about the Snellen's chart, because we know this is the basic chart that is used in the clinic for determination of the visual acuity of the patient. So the Snellen's chart was developed by Professor Hermann Snellens in 1863. As you can see in this picture, it actually consists of a series of black letters, okay, and they are arranged on the whiteboard in lines. And you can see these lines as you go down the chart, the size of the letters is progressively diminishing, right? So At a given distance, each letter will subtend an angle of 5 minutes at the nodal point of the eye. So that is why I was telling you what is meant by the visual angle, because these letters at a particular distance, they are also going to subtend a particular visual angle, and that visual angle for Snell's chart is about 5 minutes. So let me explain it to you in detail. Now, each letter on the Snellen's chart is actually called an optotype, and each optotype is made in such a way that it fits a square, right? So if you take a square like this, the letters have to fit in the square. Okay, so that is the reason why we are not using all the alphabets. There are certain particular alphabets only which can actually fit in a square configuration. Only those are taken in the Snellen's chart. Now, the letters in the Snellens are actually devised or designed in such a way that they have a breadth that will subtend an angle of 1 minute at a nodal point of the eye in a particular distance. Suppose, so this is a letter E, and you can see each part of this letter E. Suppose if you consider only this part of the letter E, this will actually subtend an angle of 1 minute of arc, right? Now, the entire letter, however, if you take, will be subtending an angle of 5 minutes of arc, right? So each letter is designed in such a way that it fits a box or a square, and the sides of each letter are actually 5 times the breadth of the constituent line. So the constituent line, say, is 1. So if this is 1, the entire thing is 5. So if this is 1, the entire thing is about 5 minutes of arc. So this is how each letter is subtending an angle of 5 minutes of arc at the nodal point of the eye. So that is very important. Now the question is that at what distance are they subtending that angle of 5 minutes at the nodal point? So each letter with its height or size is devised in such a way that, for example, the topmost letter, which is written suppose 20 by 60. Okay, so 20 by 60 means that the topmost line will be able to subtend an angle of 5 minutes of arc at a distance of 60 feet only. Okay, and the 20 by 40 means that this letter will subtend an angle of 5 minutes of arc at a distance of about 40 feet, and this small letter, that is 20 by 20, will be able to subtend this at 20 feet. So that is very important. So each letter is going to subtend that angle of 5 minutes, which is taking the arbitrary for the Snellens at a particular distance only, and that distance is represented in the denominator of the chart. So now there are two notations for the Snellen's chart. So we have the metric system, in which we use the 6 by 60. So the top letter is the 6 by 60. Then we have 6 by 36. Then we have 6 by 24, 6 by 18, 6 by 12, 6 by 9, 6 by 6, and 6 by 5. Okay, so the denominator means that each letter, that means this letter H, will be able to subtend a nodal point at the nodal point 5 minutes of arc at the distance of 60 meters only, and 36 means at a distance of 36 meters it will subtend that angle. Similarly, we have another system in which we use the units feet. So we have 20 by 200, 20 by 100, 20 by 70, 50, 40, 30, 25, and 20 by 20. So this chart over here is actually comparing the feet system with the metric system and its equivalents. Now the question is, why is that testing distance of 6 meters or 20 feet taken for testing in the Snellen's chart? So the testing is basically done at 6 meters. Okay, this we all know, or it can also be referred to as 20 feet from the target. Now the reason we are doing it is because at this distance of 6 meters, it is considered that the divergence of the rays is very less, and most of the rays which are entering the eye, they are entering parallelly. So that is what we want in refraction, the rays to come at a parallel distance in a parallel way, and therefore we are using this distance of 6 meters. So now the question is, what does it mean by 6 by 6 or 20 by 20? So before that, I will tell you what is meant by this notation. So if we consider this 6 by 6, okay, yeah, yes, so here 6 by 60, the topmost line 60 means that the topmost line. 60 means that a person who is having normal visual acuity will be able to see this line even at 60 meters. So that means although we are testing the patient at 6 meters, this patient is able to see this line even at 60 meters, right? So if someone is having a visual acuity of 6 by 36, it means that this patient is able to see this line even at 36 meters, although we are testing at 6 meters, okay? So that is what is the meaning of the notation. Now, what if someone can see 6 by 6 or 20 by 20? 6 by 6 or 20 by 20 means that he has almost perfect visual acuity. That means he's able to see that 1 minute of arc, which is close to the theoretical diffraction limits. That means we know that each letter, the width is about 1 minute of arc, and the entire thing is about 5 minutes. So even that 1 minute he's able to resolve. So that is a very good visual acuity. So as I told you, the distance, now let us see how the patient is actually tested. He's tested at a distance of about 6 meters. So let us see how. So patient is seated at a distance of 6 meters from the Snellen's chart. You already know why. And then the illumination of the chart is also very important. It should not be less than 20-foot candles. And now the patient will be tested with each eye separately, one eye at a time. And the visual acuity is recorded as a fraction. Usually the worst eye, the eye with the worst visual acuity, is tested first. Now the visual acuity, as I told, is tested in fraction in such a way that the numerator will actually tell you the distance at which the patient is currently present from the chart, okay, which normally is 6 meters, and the denominator will tell you the smallest letters that the patient is reading accurately. So if the person gets a vision of 6 by 6 say in right eye and 6 by 24 in left eye, what does it mean? It means that the patient was standing at a distance of 6 meters, and by standing at a distance of 6 meters he's able to read this line over here. Therefore his vision is 6 by 6, okay? That means his vision is almost normal. Now what about this in the left eye? In the left eye, standing at 6 meters, he is able to read only up to this, and therefore the visual acuity is 6 by 24, okay? So if a normal person stands at 24 meters, he will be able to see this line. However, this patient is able to see up to this line only at 6 meters, and therefore this is definitely a compromised visual acuity, and this is 6 by 24. So I hope that it's clear how to represent this in the form of fraction. Now, what if the patient is not able to see this line as well? So if the visual acuity is 6 by 60, fine. But what if the patient tells you that he cannot see even the topmost line? Then what do? You ask the patient to get up and walk towards the Snellen's chart till that line becomes clear. Now, depending on the distance at which the patient is present from the Snellen's chart, you are going to give him the visual acuity. As I told you that the numerator will tell you the distance from the chart. So if the patient is standing at 5 meters and is able to read the topmost line, then the visual acuity will be 5 by 60. If he's standing at 4 meters, it will be 4 by 60, 3 meters, 3 by 60, 2 by 60, and 1 by 60. Now, what if the patient is not able to identify even at 1 by 60? Now, next, what do? Now, you have to show the patient your fingers and tell him to count them. So that is called counting fingers. And this is again done at different distances. So if the patient is able to do at 3 meters, it is called counting fingers 3 meters. If he's counting the fingers correctly at 2 meters, it is CF 2 meters. Then if it is at 1 meter, that's CF 1 meter. And sometimes you might have to go very close to the patient face and show your fingers, and that is called counting fingers close to the face. Now, sometimes the visual acuity will be so worse that the patient will not be able to count these fingers even close to the face. Now, then what do? Then you have to move your hand to and fro in front of the patient, and that is called hand movements. So by moving the hands, you're asking the patient whether he's able to perceive at least those hand movements, and if he's able to do that, then that is called hand movement positive. If not, it's called hand movement negative. And then again you proceed to show the patient light. So it is believed that even in the worst visual acuity, at least the patient will be able to perceive the light sense and will be able to tell whether the light is being shown into the eye or not. And mind you, this has to be tested again uniocularly. You have to ask the patient to close his one eye properly with his palm, not with the fingers, because then the light can pass through the fingers and the patient might be giving you a false positive response from the other eye. So in this, you shine a light in front of the patient eye and then ask him whether he's able to perceive the light. And here it's often advisable to use the brightest source of light, and it is usually said that the light coming from the indirect ophthalmoscope is the brightest source that you can use for testing the perception of light. Okay, so if the patient is able to perceive the light, he is given PL positive, and if the patient cannot perceive the light, then it is recorded as PL negative, that is perception of light negative. Next, suppose if the patient is not able to do even PL positivity or PR, usually, or to tell you, the PL and PR, that is the perception of light and projection of rays, are usually tested together. That means if the PL positivity is there, suppose if the patient has PL positivity, then what you do is you take a light and then you shine it in all the direction, in 4 directions of the patient, and ask the patient to point out to you from which direction the light is actually coming. So this way you are actually testing the 4 quadrants of the retina, and then you are going to give the report. So if the patient is PL positive, you shine the light at 4 quadrants, and suppose the patient is able to see the light which is coming from superiorly, you write as PR plus. That means the projection of rays is coming nicely from the top, and then from the right side, from the left side, that means nasal and temporal, and also from the inferior. So the notation can be given like this. This is how you represent the PR, projection of rays. Next, coming to the decimal notations. Yeah, sometimes the Snellen's fraction can be converted to decimals. So that is how you give it. So 20 by 20 will be about 1, and 20 by 30 will be 0.7. So this is just a basic division. 20 by 40 is 0.5. Now for the research purpose, we have another chart, and that is called the logMAR chart. Now this is used basically for academic and research purposes and not so much in the clinics. This is a modification of the Snellen's chart. So how is it modified is that in Snellen's chart, we know number 1 is that each letter is subtending an angle of 5 minutes of arc at the nodal point. However, here the minimal angle of resolution is actually changing in each line by a unit of 0.1 log unit, right? And they have an equal number of letters in each line, and this is tested at a distance of about 4 meters. In contrast, the Snellen's is using a testing distance of about 6 meters. So that's important. So you can see about every line has about 5 letters. Okay, so the number of letters are same. However, the visual angle that they are subtending will keep on differing from the previous line by a unit of 0.1 log units. So this is the comparison between the feet notation, meters, and the logMARs of the Snellen's and the logMAR. So you can see 20 by 20 is 6 by 6 in the metric notation of the Snellen's, and 0.00 in the logMARs. So that's all for today. Thank you and have a nice day.